last but not least, it's Chris Limbach from Texas wanted to be here, and I saw that Stanford logo on the top left. I thought he was from Texas. So anyhow, Chris is on the Zoom call and is going to take us down with particle beams. Thanks.
All right. Yeah, thank you very much. I just want to say thank you to the organizers for allowing me to cap off a wonderful afternoon of talks. I've been very interested in all the previous presentations, and also to give me the opportunity to present over Zoom. I would have much preferred to have been there in person. I'm a Wildcat, as is my wife, also an Aggie now, of course, but former Wildcat, and I had been looking forward to coming back to Tucson, but I'll have to catch it next time around. So today I'll be talking about a propulsion concept that we've been looking at here at Texas A&M, and also with my collaborators at Stanford for about 3 years now, through a combination of NIAC Phase 1 and Phase 2 grants. So here at Texas A&M, myself, my group, Hayden Morgan, who's a master's student, Rohan and William Hodges, our undergraduates who've been working on the experimental part of the project, and then our collaborators at Stanford, Ken Hara, and his group have been looking at simulation, some of which I'll show you today. And so we've been looking at this combined laser and neutral particle beam concept, and today I'll be talking about some of the key phenomenology that we've been researching and have discovered through the last few years, and how these two beams are interacting with one another. Next slide. And so for the first part of my talk, I'll introduce the basic phenomenology of our concept, and then the second part talk about some of the recent simulation results. Next slide. And so as you know, the title describes, this propulsion concept is a combination concept. So there have been some previous work in this area. I know that Jordan Kerr had some concepts related to using laser propulsion, and then using that to propel spacecraft, light sails, which then accelerated other spacecraft. But really, we're looking at combining two beam approaches that have been talked about, you know, throughout this conference. One, photonic propulsion. So we're utilizing the momentum of the laser field itself, and then particle beam propulsion. And there's been a number of works looking at everything from droplets to plasma beams to neutral particle beams. And so what we want to do with our concept is really combine the two. So combine a laser and a neutral atomic beam. So it's not plasma, it's just neutral particles, just like the air in this room. And combine them in such a way that we're able to leverage an interaction. And really the central part of what we're looking at is trying to develop an interaction between these two beams, which will give us some interesting physics, which we can use to improve the propulsion capability. So it's not a linear, you know, overlap, but really we're trying to tailor an interaction which allows us to do more in terms of our propulsion capability. Next slide. And so the genesis of this, by the way, was really inspired by some of the work on laser propulsion, in particular the breakthrough Starshot, and really about, you know, 2017 timeframe. I was kind of thinking about, you know, something I had recently read on it, and I was thinking to myself, wow, you know, the real issue, or one of the real issues, is diffraction, right? So that's why you need these huge laser arrays. It's why the light craft needs to have such a large, you know, collection area. But what if we didn't have diffraction, right? So what if you didn't need a large transmitter array, or your spacecraft didn't have to be, you know, large itself, and you could just, you know, keep pushing on the spacecraft with the beam for a very long time, right? So that would eliminate many of the constraints that we currently have on the size, weight, and power of the whole system. And so that was really the genesis. And of course, in vacuum, you know, there's not too much we can do about diffraction. It's going to happen. Nature does not like gradients of anything, and will seek to eliminate them. And that's true, by the way, not only for laser beams, but also particle beams. So there's thermal motion associated with the particles that we're sending into vacuum, and they spread out. And so the A and B pictures here kind of show that as the spacecraft goes farther away, those beams spread out, and you capture less and less momentum as you get farther away. And what we'd like to do is, again, engineer this interaction that will eliminate or mitigate diffraction and allow you to use a smaller transmitter and be able to have a well-defined collimated or focused beam with which to propel a spacecraft. And if we can achieve this, We have several advantages that are shown on the upper right. Another one is that you get somewhat better thrust to power ratio using particles as opposed to photons in terms of the propulsion. Of course, there's many challenges, and we've been working to address those through our phase 1 and phase 2 NIAC projects. Next slide. And so with this type of propulsion architecture, the mission looks like this. Yeah, so you start with an acceleration phase, and just like laser-based propulsion, the acceleration phase for an interstellar mission is going to be on the order of about an hour or so, over which the spacecraft travels about half an AU. And then most of the mission is the interstellar cruise phase, and then a short flyby and transmission. And there's been really interesting talks today about each of those different phases. And so what we're trying to do is focus on the physics and the dynamics of that acceleration phase and how these two overlap beams are going to interact with one another as they go out through the interplanetary medium, and trying to understand what kind of parameters do we need these beams to have in order to have this mutual interaction. And I'll be talking about two key phenomena. One is optical guiding. So we want to use the particles like a waveguide, an extended macroscopic optical waveguide. And then the other piece of this is the optical forces, which are generated by the laser beam and interact with the particles in some way in order to keep them from spreading out into the vacuum of space. And so we've been focused primarily on developing a physical model, so a simulation capability for this process, as well as looking at stability, which I'll talk about today. How stable is this to perturbations? Next slide. So phenomenology, how does this concept work? Next slide. So one of those key effects, which I just mentioned, is refraction. And I think many of you are familiar with this. Certainly when I was a student in Tucson, there were many hot days where I observed scintillation. I can't say I saw a mirage myself, but I think many of you are familiar with this. Certainly in Texas, I see it a lot. When thermal perturbations are present, right? The density of the air changes, the refractive index changes, and so you get optical phenomena as seen here in the jet exhaust. This also works for other fluids, by the way. So there's a great display here, the picture on the left of a company that sells basically light shows. So you have a LED which injects light into a very uniform laminar stream of water, and you can see that illuminated. And so there's a lot of precedent for having changes in flow density, right, result in the guiding or refraction of light. And for the concept we're looking at, we actually need to look at very rarefied density. So we're not talking about a lot of mass that's sent out in the atomic beam, and yet we're able to guide light. And one example of that is some recent simulations done for atomic clouds. So these are very low density, 10 to the 12 per cubic centimeter. That's about 6 order of magnitude below atmospheric density. And you're able to see these very strong guiding, and you can actually have anti-guiding or kind of an expansion of the beam rather than a guiding effect. And this is all because we can exploit resonant phenomena of the atoms that we're looking at. So in this case, it was rubidium atoms. And so in order to quantify how strong that interaction is, we've been using this characteristic parameter, the V number, common in fiber optics, which is basically a measure of how strong is the refraction compared to the diffraction. And if the V number is of order 1 or more, that says that there's enough refractive effect to keep the light from spreading out, and it can be guided through the atomic beam, right? So this is a gaseous beam of neutral atoms. Next slide. The other key phenomena is this optical forces, and these were made famous in the 80s and are commonly used for confining atoms in cold atom experiments, looking at fundamental ultra-low temperature physics. We're talking about microkelvin, millikelvin, and it turns out that there's forces when you overlay a laser field with the atomic atoms themselves. There are forces which develop, which either pull the atom toward or away from the high intensity regions of the laser beam. Click really quick. And so that shows just a little simulation of what it would look like. So the atoms want to come toward the high intensity part of the beam. And again, there's a key parameter which we need to take into account when we're thinking of how strong this interaction is going to be. It's essentially the depth of the potential from which the forces can be derived relative to the thermal energy scale. And as long as that potential is deep enough relative to KT, the atoms are going to be strongly affected by the laser, and we can effectively trap them and prevent them from expanding out into vacuum. And there's been some previous work back in the 70s actually showing you can do this with atomic beams. And so this is from a paper showing that when you overlay a laser and sodium beam, you can actually see an intensification of the atoms as they're being channeled toward the high intensity part of the laser beam. Next slide. So we've been looking recently at the dynamical interaction, right? So you have these two systems interacting with one another. They're essentially overleaved with one another. And so how are they going to interact, and what kind of physics do we expect to result from that? There's been some great work looking at cold atoms in the lab. So this is stationary atoms, but having the fundamental physics, which I just mentioned. So you have a laser propagating through those cold atoms that produces a phase modulation, so refraction of the laser. After some distance, you back reflect that back to the cold atoms, and this produces an intensity modulation, which the atoms then respond to. And so there's a key feedback loop there between the laser propagation and the atomic motion. And what has been found, this is some work out of Laborie, and what they've shown is that you can see this very interesting spontaneous pattern generation. This is a hexagonal pattern which is formed due to that interaction. So the atoms come to some equilibrium distribution, and so the laser as well. And you get this interesting dynamics, and there's a critical threshold, it's like a spatial threshold for when the system will become unstable. And we wanted to apply the same analysis to our particle beam. Next slide. And so we've gone through, this unfortunately something went wrong in the transfer here. But suffice it to say, the figures are messed up, but we performed this analysis, and this was really motivated in part by some comments made, I think, at the last TVIW by Gerald Jackson, who said, we should do the stability analysis. It's not as trivial as, like the two-stream instability with the Poisson equation, but nonetheless, this motivated us to actually go and do this analysis, and out popped another key parameter, which is related to the dynamical interaction of the laser and the particle beam system. This is this parameter tau. And let's see if you go to the next slide, what happens. Oh yeah, okay. So all the figures are messed up, but so this parameter tau is actually really important because it tells us something about how the atoms in the laser beam are going to affect each other. So as this feedback loop keeps going, diffraction, and then the motion of the particles, and then more diffraction, how's that going to happen? Well, it depends on whether the relative angles between the thermal motion of the particles, kind of thermal spreading, and the diffraction of the particles. And what we found, which was really quite interesting, and you can't really see it from this figure, is that there's a wave number, so a particular spatial scale, where at higher frequencies, you can actually damp the motion or the disturbance which is introduced into the system. And so what this figure is supposed to show is that when we introduce a disturbance in the field, in the laser beam, it actually becomes damped. And the mechanism by which it becomes damped is that you end up having a series of resonant particles which are traveling in certain preferred directions, basically when tau is equal to 1 here. And those resonant particles are able to kind of take that perturbation and the entropy of that perturbation and put it into the kinetic distribution function, so the velocity distribution of the particles. So so we have a upcoming PhysRev paper on this, which has the correctly formatted figures. So please take a look at that. Next slide. And so moving forward, so this is a really interesting result, right? That there's actually a mechanism out there which can act to stabilize the beam and damp out any perturbations in that intensity profile we might have. Next slide. So moving on to the capability, I'm going to go through this quickly. We did some calculations for our phase 1, which showed that we really can potentially achieve up to the kilogram level payloads for an interstellar mission on the order of 0.075 C or 7.5% C. The capability scales very strongly with the final velocity, so we actually get a big benefit from going just a little bit slower. And we wanted to see, well, this is based on those key phenomena I mentioned earlier. What happens when we actually simulate the dynamic interaction of these two beams? Next slide. And so we built a physical model. Let's just including all the phenomena I just mentioned. Next slide. And we wanted to look at the coupled propagation. So can we, by combining these two beams, create a self-guiding effect which allows us to propagate them farther than diffraction alone would allow them to. Next slide. And so this is some work, of preliminary work out of the group at Stanford, Ken Haro's group. And what they did is they built this simulation capability and injected two Gaussian initial profiles, so a Gaussian spatial profile, and then varied the density of the atoms. And as you vary the density of the atomic beam, this basically sweeps through a range of this V number. So it changes the ratio of refraction to diffraction as these beams co-propagate. And what they found is quite interesting, that there's actually an optimum density or an optimum V number with which to co-propagate these two beams. And that's close to what's known as the critical density, which gives us a V squared of about 2.4. And so at this distance, we get, as you can see, we get very long distance propagation. This is many diffraction lengths. But as you go to very much higher density, that increases the refractive effect, and you end up getting a pinching effect which occurs. So you kind of focus down much faster than you want to. And what this does is it transfers a lot of energy and kinetic energy to the particles, which are then ejected. And so there's a mechanism that's at work here, which is a dynamical heating. It's the interaction between the two beams which heats the particles and ejects them. And if we can what this shows is that if we can minimize that dynamical heating, then we can potentially get farther and farther distance propagation. Next slide. So I think I need to wrap up and give some time for questions, but the next step is we've actually built a capability to determine particular profiles of the intensity and atomic density, which allow us to minimize the dynamical heating. And that is our next step, is to use those as the initial condition to propagate further. Next slide. And so this is the summary, and I'm going to leave it there and allow the audience to ask any questions. Thank you. I'll have to get the correct version of those slides, the correct rendering for the final final PDFs which are sent out.
Thank you, Chris.
You also, it's a paper by October 1st, so you can get the right figures in the paper.
Exactly. There we go.
I have a couple of questions here which I'm going to combine because they're kind of similar. Can we use this laser particle beam approach for interstellar comms? And are there any weapons applications for this technology? Both of these, I think, have to go with range before decollimation.
Sure. Yeah, I mean, so the comms, I thought a little bit about the communications, because there's a lot of interesting things that could be done with communications. I think the real issue would be that number one thing to consider is that you are using some mass, right? So the total amount of atomic mass that you need to actually do the whole mission is something on the order of maybe 10 kilograms, which actually isn't that much when you think about it. But if you're communicating for a very long time, that's 10 kilograms is for the hour of acceleration. If you're communicating for a very long time, you may end up needing a lot of mass. So that's kind of the number one thing to think about. And then the second concern would be basically centrifugal force. So if you're in the solar system, you have to worry about all of the forces from the many bodies that make up the solar system, right? So as you send out your combined beam, if there's reference frame effects, as you're trying to point somewhere, you may end up having those beams kind of curve off to the side, right? And that in turn provides an additional consideration on what those parameters need to be to avoid basically decoupling the atomic beam from the laser beam, because of course the photons are traveling at the speed of light and the atoms are traveling at something less than that, and so that's another consideration. Oh, and then the weapons. So I think it was maybe a year or so ago that Mike Griffin, in his capacity, decided to de-emphasize long-term development of kind of particle-based weapons in space, and to my knowledge, that has not changed. But if anyone knows that it has, please let me know.
Thank you. And one more question. Does the Landau damping mechanism create a dynamic radial aperture that causes particle and photon loss at the radial edges of the two beams?
Yeah, that's a great question, and I'd be interested to know the answer. So the analysis we've done so far has been basically a plane wave as the baseline state, and so we haven't done the analysis with axisymmetric beam because we just haven't gotten to that yet, and we have to input the profiles actually that I showed, the stationary profiles for the laser and atomic beam, and do the stability analysis around those profiles. So we haven't done that yet. I think it would be interesting to look at that going forward, but it's something that should help answer that question that was asked.
Okay. Chris, thank you. Appreciate it. That was great. We look forward to seeing you in person next time. So thank you.
Me too.